recap the concept of relative motion, we had seen that the various parameters given like this, the relative position of one object with respect to another was given by the difference of positions in the ground plane, the relative displacement, therefore was the difference of the absolute displacements in ground planes. The relative velocity was the difference in absolute velocities, and the relative acceleration, the difference in absolute accelerations. So these were the concepts related to relative motion. Now today we will discuss an important example of relative motion. Relative motion applications. In case of swimmer or a boat, whichever be the case, moving in flowing water.
Sir, I guess we have covered this application in last
Yes,
class
sir.
only.
We have done this the rain.
In the last lecture, is it?
Yeah, sir.
Yes, sir. We compared the velocity of boat is equal to relative velocity plus velocity of water.
Okay, just a second. Just go through what we discussed. All right, we have had the third lecture of relative motion. Okay, so we are done with all this. So today it's not the third lecture; it's the wind up of kinematics. So okay, we'll do a couple of examples of this. Okay. Then we'll start with the next section. So I guess most of you have completed HC Verma for relative motion, right? The swimmer river type of problems in HC Verma. You have discussed the doubts in the last doubt session. Are there any questions pending? Okay, so let's do an example problem. So here what is happening is the flow velocity of the river the water flows at 4 kilometers per hour. And what is happening is that a swimmer is moving like this with respect to the water. So a swimmer moving at 5 kilometers per hour with respect to still water. It starts from the point P. Such that his relative velocity starts from point P at time t equal to 0, such that P swims in a direction at theta equal to 37 degrees with respect to the perpendicular to the flow. If the width of the river is 240 meters, find the distance traveled by him with respect to ground frame and the time taken to swim across. Just try this problem to do. So that 5 kilometers per hour vector shown is the velocity relative to the water, or it is the velocity with respect to still water. The net velocity, as you know, will become the vector sum of that with the flow velocity. So first of all, determine what that net velocity is in terms of direction also, not just magnitude, so that you can understand that what is the actual line along which he will be moving in the ground frame. Okay, people. So the question is clear to all of you. No, Vedant. The thing is, he will not swim in the perpendicular direction. His net velocity will have a component which is downstream also. Let's understand why. Theta is given to as 37, and that theta is with respect to the perpendicular. Take this as our y-axis, this as our x-axis. What we can see is that the relative velocity of the swimmer with respect to water is this vector. Yes, that's correct, something like that. So the drift actually will be 1/4 of 240, it will be 60. I'll explain how that comes. So this is the velocity of the water in the ground frame, which is 4 kilometers per hour in magnitude. So when we calculate the vector sum of these two, we'll see that it comes out to be something like this. It has a drift component also. You'll end up moving something like this. This will be the net velocity of this swimmer with respect to the ground frame. So even though the swimmer's body is oriented like this, he'll end up drifting like this. Eventually reach somewhere there. Some time. Okay, so let's understand. So we can write the water's velocity in the ground frame as a vector as 4 I cap. We can write the velocity of the swimmer with respect to water as 5 minus sine theta I cap plus cos theta j cap. The theta is 37 degrees, so it is as you can see, it is not able to cut the drift because okay, the velocity of the water is +4 and this is -3. So the net velocity of the swimmer in the ground frame, the sum of the relative velocity plus this is I cap plus 4j cap. So now what you do is from time 0 to capital T, the displacement of the swimmer is this net velocity into time. So the displacement, because this width is 240, let's say this drift is a value that we don't know right now. So this is E I cap plus 40 J cap. It's going to be I cap plus 4 J cap. This is in kilometers per hour. Yeah, this is in meters. From this equation, you can see So the actual distance he's swimming. In this case, it will be magnitude of the displacement. This will be the distance. And this will be the time in which he covers.
So we can leave this displaced distance in vector form also, right?
Sorry, come again. We can.
Leave this. No need to find the magnitude, like because it's
No,
I got.
because, in the question actually I had asked you to calculate the distance traveled. Okay, so
Okay, so I found the like this distance vector.
it's okay. So that's the method only. First you will find the displacement, and then if the question is asking you for the distance traveled, then you just calculate the mode of that.
Yes, sir. Okay.
So here I have calculated the mode finally because the question asked that. That what is the distance traveled by him with respect to ground and the time taken. Whereas a different question might ask you.
Scroll down.
So hope this question is clear to all of you. Okay, let's move on to another type of situation where we use this concept. Okay, that's very same concept, but in a different situation. You can have an example where you have an aeroplane. Again, moving with wind or breeze. So again, the concept will be like this, that the velocity of the plane in the ground frame will be equal to the relative velocity of the plane with respect to air plus the velocity of the air. So this is the net velocity of the plane with respect to ground frame. And this quantity, this here, becomes the plane's velocity with respect to air, or you can say plane's velocity in still air. Had there been no breeze or no wind, whereas this is the air velocity due to wind or breeze. Okay. So this concept. Okay, so Now this shows us the geographical directions. Now in this position A here, there's a position B over here, and this is, so B is a city at a distance of 800 kilometers at theta equal to 37 degrees north of north of east with respect to city A. Now there is a wind at 20 kilometers per hour. So there's too much wind speed. Let's say there's a wind at something like 5 kilometers per hour along west. Now, an aircraft has an airspeed of 250 kilometers per hour. So first of all, what is the direction of its velocity with respect to air, so that its path is along AB. So here you express it as an angle with respect to the line ABO. Second, the time taken from A to B. Now, I mean, this is a hypothetical question because you're just assuming the aircraft goes at constant speed from A to B, whereas in reality, it doesn't happen that way. And also in reality, that in a journey like this, the airspeed, the wind velocity will change in between. It can't remain constant. So there are like two huge simplifications of a real life situation here. But this is just for your application of relative motion concepts. Just try out this question, people will discuss. So you have to apply the same equation. This is like that river water kind of problem only, but instead of the water flowing, it's now air moving at a wind velocity. And instead of a boat or a swimmer, it is the aircraft that is moving, or the plane which is moving at a certain given velocity with respect to the air or in still air. Okay, so this type of question, because of the vector algebra involved, we'll take slightly different approach. So when we are resolving the vectors, we will not take our x and y axis along the direction shown of north, south, east, west, because that would make it very difficult in terms of solving the vector algebra. Okay. So instead of taking this as our system of axis, we will take the direction along which that line AB is. We will think of that as our x-axis, so that our net velocity has to be along that axis. So that will make it easier to solve. And since the question has also asked for the direction of the net velocity, or rather the direction of the aircraft with respect to air, in terms of an angle with respect to the line AB, it's going to be easier this way. Okay. So if this is the velocity of air, it's a very small vector in comparison, 5 kilometers per hour. Then to keep the velocity of the aircraft in the direction of the line AB, what we'll have to do is we'll have to orient the aircraft in this sort of direction. Its velocity is actually many times this velocity. So it's a little difficult to show that in a vector diagram. But this is 250. So it is at some unknown angle theta right now. This is the velocity of the plane with respect to the air. So that now the vector sum of these two should become along this. So this is what we want. The net velocity of the aircraft should be along this line. Okay. So the simple solution to this is that if this velocity is along AB, that is what we have taken as our x-axis, it implies that BA sine 37 should be balanced by this sine theta. And secondly, so you can understand this, how it's happening, by just thinking that you're resolving this. So how we are getting these equations, that if we resolve these vectors, it's an expression like this. Now this term, we want it to be 0, so that the net velocity is only along this direction. So that's how we are getting equation 1. And then the net velocity becomes this, so that's coming in equation 2. So from equation 1, you can see that sine theta is VA sine 37 divided by, okay, so it is 5 into 3 by 5 divided by 250. So 3 upon 250. So that is, so sine theta is a very small angle. We can say that theta is approximately radians. This is the idea that for a small angle, sine theta is approximately theta and cos theta is approximately 1. So the answer to the first part will become like this, that the aircraft will have to be turned at a very small angle with respect to the line AB, and that angle is approximately 0.012 radians to north of the line AB. So the velocity of the plane with respect to air should be directed at a very small angle. The north, the line AB.
So,
Yes.
so why did you take in the first equation? Why did you take VA sine 37 to be equal to VPA sine theta?
Yeah, so that is what I've explained over here. In the second part, I've explained this. If you resolve these vectors in this way, okay, this is what is the relative velocity of the plane with respect to air. This is what the velocity of the air is. So the vector sum becomes this. Now what we want is that this should be along AB, which is our x-axis. So its y component should be 0. No?
Yeah.
So this term, put it equal to 0 and you will get the first equation.
Okay. Yes, ma'am.
Okay, done now. Now, what about the net speed of the aeroplane? So that's the first part. Now, the net speed of the aeroplane, how we'll calculate that? With respect to ground. So we have indirectly got that already. You can see, so from equation 2, but we just have to apply the trigonometry applications, approximation methods a little carefully here.
So we take cos theta as 1.
We will take cos theta because theta is small. So we'll apply that. So cos theta is approximately 1. So this will become 5 into 4 by 5 plus 250 into 1. So it will be, I mean, the approximate value will be 254 kilometers per hour. So in this case, the wind is actually helping the aircraft. Okay. Whereas if the same aircraft was turning back from B to A with that direction of the wind, then the wind would contribute to the aircraft slowing down. So that is why you will see that typically, like if you make a flight from one city to another and return to that city, there is a difference in the time. So it's not that the aircraft is typically having a different airspeed, but it's because they call it tailwind. If the tailwind is with you, then it improves the time. You can cover the same distance in less time. Okay, so this question is clear, I hope. Now we will do one more example of the situation of moving rain. I mean, a person moving with respect to rain. Okay, let's look at that example. So rain is falling like this in a slanted sort of manner. So if a person walks at 3 kilometers per hour as shown, the rain appears to be vertical with respect to him or her. Now, if they turn by 180 degrees and move at 1 kilometer per hour in the opposite direction to show, now the rain appears to be at 45 degrees to the vertical. Find the speed of the rain with respect to ground and the angle of inclination. So previously also we have done a question like this, but in that the direction of the person was not changing, just his speed was changing. So slightly different version of that question. So let's also do this for practice, and then with this we are done with the additional practice problems related to relative motion. Okay, people, so let's look at the vector diagram related to this. So in the first situation, the person is moving at 3 kilometers per hour horizontally. So this is what the person's velocity should look like, let's say. So its magnitude is 3 kilometers per hour. And the rain is falling vertically, but in such a way that the relative velocity should appear to be vertical. That means it should be something like this. So that when we draw the difference of these two vectors, so we don't know this, we don't know this angle also, but we know that the relative velocity, again, we don't know the magnitude of it, but it appears to be vertical. So this is the velocity of the rain relative to the person. So this appears to be vertical, so it should be, this angle should be 90. So this is the first situation. So now in the second situation, the person reverses their velocity. Now this is the velocity of the person. Also cuts it down from 3 to 1. So this is a new velocity, let's say with prime. Okay, but the velocity of the rain is the same as in the earlier diagram. So the same vector that you have to pick up from there. So this is the velocity of the rain. Then this angle is the same theta. It's the unknown value, unknown angle. But now the relative velocity, it becomes like this. And this is given to us to be at 45 degrees. So this is the new value of the relative velocity with respect to the person. We are given that this is at 45 degree inclination. So you have to use these two vector diagrams to find the magnitude of the velocity of the rain with respect to ground and find that angle theta. So use the vector diagrams that I've given you here to try and solve this yourself. From this point, it should be quite easy. Okay, just analyze the two diagrams and see how you can relate them. Okay, let's try the calculation. Jinendra, unfortunately, the answer is not correct. I think. Anyhow, so let's analyze this diagram. So see, in the first triangle, if this side is 3, this x is equal to 3. And whatever this relative velocity is, that's the same. So you can see that the velocity of the rain in the ground frame so the magnitude of this is y. Like this. Okay. Now in the second diagram, when we draw the velocity of the rain, this y is the same as in the first diagram. And this x is also the same as in the first diagram. This theta is also the same. Only now this angle is 45 degrees. You can see that this value is 1. And this value is y. Now from this diagram, what you can see is that 3 plus 1 upon y is equal to tan 45. So that is telling you that y is equal to 4. So plug that in back over here. So you can see that velocity of the rain is 5 meters per or whatever kilometers per hour. And this theta is equal to 37 degrees with respect to vertical. Okay, so hope it is clear. No, yes, the next chapter is going to be circular motion instead of this thing, rotational motion. Rotational mechanics will come a little bit later. Okay. Anyhow, there is one more concept in related to relative motion we have to discuss before we can come to circular motion, which is our next chapter, and that is the concept of relative velocity of approach or separation, as may be the case. Between two objects, okay, between two moving bodies. So this is slightly different to relative velocity, okay, because this is what we call approach velocity or separation velocity. So if two objects or bodies, whatever, or particles for that matter, are moving such that at a given instant of time, the distance between them is decreasing. Then they are said to be approaching each other with a certain instantaneous, that means at that instant, approach velocity, which we denote with this symbol V. Okay. And similarly, if the distance between them is increasing, then they have they have an instantaneous separation velocity. Okay, so let's understand how this works now. So suppose we have a situation that at a given instant of time, there are two particles A and B like this, and they are having velocities like this in the ground frame. So two particles directly approaching each other in one-dimensional motion. So in this case, what will happen is that the distance s between them is decreasing with respect to time, such that the approach velocity is equal to VA plus VB. It's easy to understand because what is happening is, if this is the picture at some time t, then we can see that after a short amount of time, what is going to happen is that, let's say A will be somewhere here and B will be somewhere here at time t plus delta t. So the distance between them would have decreased from s to s minus delta s. And you can see that delta s would be, so s is decreasing at the rate like this. Okay. But now suppose we have a different situation where something like this is happening. Now the two particles that we have, suppose they are moving in such a way that B is actually moving opposite or away from A, and A is moving directly towards B. Suppose this is 6 meters per second. So now if I ask, is A approaching B or are they separating?
They're approaching.
They are approaching, you can say. Okay. And find the approach velocity or the separation velocity, whichever be the case. Let's do another version of this same question. Yes, Vedant, that's correct. Jinendra, that's correct. Now, what about the B part?
So they're separating.
Yes, in B part, you can see the distance between them will be
increasing because B is moving away at 16, whereas A is approaching B at 10. So between the two of them, as far as relative motion is concerned, there is a separation happening at the rate of 6. So for this part, they will have an approach velocity of 4 meters per second. They are coming closer to each other at that rate. For this part, they will have a separation velocity of 6 meters per second. You can just visualize this kind of situation that I've drawn on this side to understand why they are approaching or why they are separating. After some time, the distance between AB in the first case, A would have come closer by 10 delta T, B would have moved further away by 6 delta T. So overall, the distance between them has reduced by a factor of 10 minus 6. That is 4 into delta T. Similarly, in the second case B, you can see that distance would have increased between them. Okay. So this is the easy case of this application of separation and approach velocity. Now we come to the slightly more involved version where there is motion in 2 or 3D. Okay, now let's see the more complex situation. What if something like this is happening, that If this is the line joining the two particles at a given instant of time, but they are not moving along this line, at least not both of them. Okay, so suppose what is happening is that before that, let's also look at one example where they are actually separating from each other. Oh, we have seen that example. Okay, so suppose this is moving with a velocity like this. So this has got a magnitude of 15 meters per second at an angle of 37 degrees, whereas E is moving like this. The magnitude of, let's say, 8 meters per second. So the question here is that are A and B approaching or separating, and find the instantaneous approach velocity or separation velocity, as may be the case, at the given instant. So what we have to understand in this kind of situation is that suppose we take a designated coordinate system where A is lying at our origin of the coordinate system at time t, which is shown, moving with a velocity of 8 meters per second like this. B is located at some coordinate x equal to x at time t, moving at this designated velocity of 15 meters per second at this angle of 37 degrees. Okay, so then right now the distance between A and B, so at this instant t equal to t, the distance s, that is between A and B, is equal to this x coordinate that B has. It is like the x coordinate of B minus the x coordinate of T. So right now x. Okay. Now what is happening is that BA is equal to 8 I cap. That means E's x coordinate is increasing at the rate of plus 8. And VB is equal to minus 15 cos theta I cap plus 15 sin theta j cap. So it is minus 12 I cap plus 3 j cap in meters per second. So what this tells me is that
So it will be
the
9.
rate at, sorry, 9. Yeah. So what this tells me is that the rate at which B's x coordinate is changing is minus 12. Whereas the rate at which B's y coordinate is changing, that is plus 9. Okay. So these two are the important things here. So the instantaneous distance between them, x, is xb minus xa. So the rate at which this is changing, dx by dt, is this rate. So that here becomes minus 12 minus of plus 8. So the rate at which the distance between them is changing, ds by dt, is minus 20. So they are having an approach velocity. They are having an approach velocity of 20 meters per second. Okay. So we'll just understand this in a more simple way when we come to the final formula. But this is the calculus method of understanding the logic rules. Okay. And the final formula, what we'll do is, we'll see that this velocity of B has to be divided into two components. This is VB sine theta. This is VB cos theta in this case. Okay. So I've broken this into components. This is VA. So you can see that at this particular instant, if the distance between them is S, so minus ds by dt is equal to VA plus VB cos theta. So that will become an approach velocity of 8 plus 15 cos 37 degrees, so that will become 20. So what we are understanding in this diagram is that at this given instant of time, this is at this time t equal to t, because this angle here is 90 degrees. Okay, so this component VB sine theta, it's perpendicular to the line joining AB, so it does not play any role in the approach velocity. Okay. So at the given instant, the component of B's velocity perpendicular to the line AB does not contribute to approach or separation, whichever be the case, velocity. So that is why our approach velocity becomes BA plus BB cos theta, which is 20 meters per second. The BB sine theta component does not play any role. This perpendicular component, this is the component BB sine theta. So this does not play any role. Okay, whereas the component which is along the line AB, that is the one that plays the role in the approach and separation. Okay, so this is the situation where we're looking at a 2 or 3 dimensional type of motion of two objects, and we are looking at the approach and separation velocity. So just make a careful note of this concept. Now this approach and separation velocity concept becomes important not only for solving kinematics problems, but also for solving certain other types of situations in physics like constraint relations, etc.
So means in this case, we are just gonna compare like the initial distance, and then we have to check that like rate and change of distance in that initial frame only, not the extra one.
Okay. Sorry, beta, what was the question again? I missed it.
Yeah, yes. In
this case,
yeah, we have to compare the initial distance with the rate of change in distance in that frame only. Like if
at that instant, correct. Okay, in that very small time dt.
Okay, so
Basically, what is happening now, after a certain amount of time, you will see that the angle has changed.
yes, sir.
The angle at which VA and BB are lying, they have changed. And actually, even BA and BB could have changed because there's no guarantee that A and B are moving with uniform velocity. They could be moving with some acceleration, their directions could be changing. So everything changes a moment later. But at that particular instant, this is the situation that VA's direction is directly towards B, and VB's direction is at some theta with respect to the line from B to A. So we have to consider the component of B's velocity, which is directly towards A, to calculate the approach velocity at that instant. Okay.
Okay, sir.
So this is the instantaneous. So that means it's only for that instant. It will be changing after that instant. So this is the instantaneous approach velocity.
Sir,
Yes.
sir, how we will know it's approaching or separating in this case, sir, mine.
So now we'll discuss that also. Okay. How whether it is approaching or separating. Now, suppose we have a situation which is a little bit more general. Now we have a situation like this, that this is the line joining AB at this moment. And both of them are having kind of random sort of velocities. Let's say this is having a velocity of 10 meters per second at an angle of 60 degrees, let's say. And this one is having a velocity of let's say 15 meters per second. But this angle is something different. This angle is, let's say, 53 degrees. Okay. So then are they approaching each other or are they separating?
Is separating.
Approaching.
At the given instant. So you can see that what is happening is, if we just concentrate on the components of velocities along AB, because the perpendicular components don't play a role. Now we just understood this. So this component is VA cos 60. So that is equal to how much? 5.
5,
And this component of B's velocity, which is
9.
directly away, yes, very good. So this is VB cos 53. So this is equal to 9. So you can see that they are actually separating. At the given instant, S is increasing with respect to time. So the answer to that is ds by dt is positive of 9 minus of 5. So it is plus 4 meters per second. So ds by dt is a positive quantity. So they have a separation velocity of 4 meters per second. Just note down this example. We'll just take another 2 minutes. Okay. One more application I want to show you. So now an example of an application in a constraint relation. So this is a standard type of constraint relation that you would have seen as part of your Newton's laws chapter. And you might have used thread length conservation with possibly more complex calculus type of application for this. But now we'll see that how we can use let's say this object is A, this object is B. This thread is at an angle theta like this. Now at a given instant, A is moving at some speed VA and B is moving at some speed VB. So we have to find the relation between A and B. The constraint relation between A and B. So the idea we can use here is that in this diagram, forget about the rest of the things in the system. Take this part of the length of the thread to be L1 and this part of the length of the thread to be L2. This length and this length. So L1 plus L2 is the total length of the thread, which is constant. So we have dl1 by dt plus dl2 by dt should be 0. Okay. Now, if you see this point A here is moving with a velocity VA. So if I label this point as P, you can see that what is the approach velocity of A and P. Okay. And similarly, what is the separation velocity? Because B is moving down like this of B and P. So can you tell me how much this is the approach velocity of A and P?
The VA cos
VA
theta.
cos theta.
Yes, very good. It is VA cos theta. And what it represents minus dl1 by dt.
Yes, sir.
Yes, sir.
The separation velocity of this one is directly VP because it's moving directly downwards. And
Yes.
that is equal to how much? Plus dl2 by dt. So now we can substitute these here. So you can see that dl1 by dt is becoming minus VA cos theta. And dl2 by dt is plus VB. This should be 0. So directly the constraint relation is that VB is equal to VA cos theta. This is a constraint relation. So, instead of taking X and Y and things like that, other approach of doing this question would be like this, that you would take this as some fixed height.
You can also apply fully constraint.
Wait, that one only. So if this is L1, this is L2. So you take X square plus H square is equal to L1 square. And then in this diagram, if this is moving at VA like this, dx by dt is equal to minus VA. And H is a fixed length, so that is 0. And dl2 by dt on the other side is equal to plus VB. So then you would use calculus and all that. But this method is unnecessary now. Okay. Once you know this approach and separation velocity concept, you can directly apply that in a situation like this and solve it in one line basically. Okay, so we'll see some more examples of application of this approach and separation velocity in the next lecture also, but we will start with circular motion theory part in the next lecture. Okay, so you can start looking at the basics of circular motion also after completing kinematics problems. Theory wise, you can start with the circular motion either from Resnick Halliday or NCRT, whichever you're following. it's preferable to follow from wrestling calendar. So that's it for today's session, people. Wish you all the best.
So,
Bye.
Thank you, sir.
Okay. Yeah, yes, I'll scroll down also. Okay. Zooming in further than this will actually make the resolution too small.
So,
Yes.
sir, if we refer the module, is it more than enough?
Module for the theory reading, you mean?
Yes, sir. The theory and the sum-based things.
See, module is good for giving you the definitions and solved examples, but for a little bit of further understanding of concepts, it is better that you refer to some text also. So whichever is preferable, either NCRT or wrestling calendar. Okay. It's
Okay.
advisable, especially when you're doing the basics of some chapter, so that all the fundamental things are clear. Then you can refer to the module for all the problem solving tricks and methods and all that.
Yes. Thank you. Thank you, sir. Bye.
Okay, people, bye. Have a nice day.